Good evening, dear student, and welcome to this other edition of our functional analysis class. So today we will proceed with some introduction to measure theory. As I posted the notes, the slide, I will just quickly go through, and if need be. As I told you, this is just for your learning, right? I hope that, not that I hope, but I plan really to cover everything this week so that we can proceed with other stuff. But the good thing is that as we covered this measure theory, there are some aspects of the actual program that we are also covering, because remember that during this review of measure theory, we define what is a topology by open sets. And it will also give you a good idea, understanding of what we'll be doing through functional analysis, because they are related. In some way they are related. Because in functional analysis, we're talking about integral of functions, we'll be talking about open set, of course, which is already what we have to do, Banach space and all those things. So they are really closely related to what we are currently doing. So this will really broaden your understanding about functional analysis. You'll be more comfortable to read even the prescribed textbook, because to really read it, you need some background. I hope that after this, it will also allow you to understand how things are defined, why you are doing this, why you are doing that. Okay, so without any further ado, let us quickly go through the slide. If I can spend 30 minutes on this, I'll be happy. But I think in the next lecture, I just need to briefly define what is an integral, and then from there I will quickly define what is LP space. But I will not go into too much detail. As I told you, this is a full semester module. So if you need more understanding, if you're interested, if you have the materials, I already gave you the link to those videos that will give you more understanding. I'm trying to go through this so that you better understand what you are watching on the internet and some of the videos. So that's the purpose. Otherwise, I could have just jumped into LP spaces and ask you, okay, just rely on what you read or you watch on the internet. But I thought that it would be good to accompany you. So that's the purpose of this. Okay. Okay, so before this, I gave you homework on the, after we define what is a measure, I gave you this homework. So, property of measure. So this also is a property already, that I this is already a property. I think, what is that? Okay, this is the definition. And I gave one, like this property. I proved this already. This is already part of properties, which you can see here. We proved this already, which is called monotonicity. Okay, so let's go through properties of measure. So we have a measure space here, X, calligraphic A, and mu. So this is a measure space. So we have these following properties. They are not exhaustive, right? There are two other properties that I could have added. I think maybe I will add it. It's also important. Finite additivity, meaning that if I have a finite set or subset of X, that is, which are pairwise disjoint, meaning that if you take two arbitrary subset, the intersection is equal to the empty set, right? Now, mu of the finite union will be the sum of the mu's. So that's what we have here. And we have monotonicity. if A is a subset of V, A and B being measurable sets, mu of A is less than or equal to mu of B. And another property also, if A is a subset of B, where the measure of A is finite, then the measure of the difference, B minus A, is equal to the difference of the measure, that is measure of B minus measure of A. And we have the countable subadditivity. If I have a countable, let's say I have a sequence of measurable set, right? Mu of the countable union of AN is less than or equal to the sum of mu AN. In fact, this is a series of mu AN. So in this, you see that we don't have information if they are pairwise disjoint, right? So this is obviously from the definition of the measure, if they are pairwise disjoint, as you can see here in the definition, if they are pairwise disjoint, there will be equality, right? They will be equal. But in the property, we just took an arbitrary collection or arbitrary sequence, which are not necessarily pairwise disjoint. So in that case, you don't have additivity, but you have subadditivity. So that's what we have here. Okay, so there are two other properties that I didn't write here. I can quickly add them. The first one is what we call continuity from below. Continuity from below. From below is like when you have an increasing, or from below. That's from below means that you have something that is increasing, and from above you have something that is decreasing. Right? If you are below, you want to reach somewhere, you have to increase. If you are above and you want to reach somewhere, you have to go down. Right? So continuity from below, continuity from above. So for that, we need like here a sequence of subset that are increasing. That is from below. Let me write here continuity from below. So for the continuity from below, you have an increasing sequence. Unfortunately, I would only do from below because I don't think I will have enough space here. From above will be similar. Okay, so let me quickly see if I can write it here. So I will write here that we have a sequence like this. Okay, I will say that it's decreasing. I will just put this so that I will be not it will not take too much space. So I take a decreasing, increasing, because we say from below. So we need an increasing sequence. Oh. So we have an increasing sequence like this. So that is that A K is contained in AK plus 1 for any key. Right, that is increasing, and the other one will be decreasing. Okay, so the property is the following. Mu of the limit of the limit, because I can put the limit here. mu of the limit of this. But mu of the limit will be in fact the union because they're increasing. Okay, but let me put the limit inside here. That's where you see the continuity, meaning that you can take the limit outside. It means that mu is continuous. So I will write here that limit a n when n goes to infinity is equal to the limit of mu an when n goes to infinity, right? Okay, but because this is increasing, this limit, in fact, this limit is the union. So that's why you will see in some textbook or definition, that, I mean, in some text here or other material, that here you write mu of the union. So this, for the sake of space, I don't want to. Okay, so this limit is equal. You can write it is in fact the union of all the an. I can put k here, k going to 1 to infinity, or you can still put n, where n goes to, when n runs from 1 to infinity. So this limit of n is the union of all the an. Okay, so let me quickly explain it here. Unfortunately, the space. If an is increasing, let's say I take a finite number here. If I take the union k going from 1 to n of ak, you agree with me that this union is an, right? Because all the ak's, a1 is containing a2, a2 also, they are all containing an. You know that if a is a subset of b, a union b is the largest. So if I take all this union, the largest is an. So the union will be an. Now you can see that from here, if I take the limit when n goes to infinity, this gives us that limit an when n goes to infinity, it will be equal to what? It will be equal to this union. It will be union ak when k, because you just turn that n to infinity. So this is infinity. But this you can still write, the way it's written, you see that this n, which is our limit, does not appear there. So we can rewrite it as union an n running from 1 to infinity. Of course, you have the impression that n is also going to infinity there, right? And you link it to this one. So that is it. So this limit n going to infinity is in fact the union. So that's why sometimes instead of seeing the limit here, you just see the infinite union, right? It's the same. Okay, so I will erase this one. This was just for explanation, to explain. Okay, so what we have just written here, we can replace, this is a continuity from below. Now from above, you have a decreasing sequence. If you have a decreasing sequence, you have exactly the same result limit. Inside, you can take it out, right, and get it. But now the limit here now will be intersection, right? It will just be intersection. So I will write that right away. So this one is continuity from above. Continuity from above. Continuity from above. So here you have a decreasing sequence. Decreasing sequence of, obviously they are all element of A. I didn't write it here, but they are all in the sigma algebra, but it's decreasing, right? So we have a k contains ak plus 1 for any key. That is decreasing sequence. Then we have this, the same thing. So we have mu of the intersection n from 1 to infinity an, which in fact is the same as this one. So it's mu of the limit, limit an when n goes to infinity. So these are equal, okay? So the continuity comes from the fact that I can take the limit from mu. I can take it out. So that's the continuity. So that is the same as limit mu an when n goes to infinity. So this is a property it's proven. It's proved. You have to prove it, but you are using it as a result. So we call them properties, right? They are properties of measure. But this is a proposition, meaning that there's something you have to establish. You have to prove it. But you are not requested to prove it. Just use it as a result in case you need. Okay, so that is it. Now we are going to define outer measures. What is an outer measure? And we will see the motivation why we need this, right? We already defined what is a measure, and we saw the properties of measures. Now, what is an outer measure? An outer measure is defined on the entire power set of the set X, which is a non-empty set. Remember that measure in general, in fact, when we define measure, we define a measure on a subset of the power set, which is a sigma algebra, even though, of course, the power set is a sigma algebra, but it's the largest power sigma algebra on X. So you take the entire power set. But in general, we don't use the entire power set. We just use subset that are sigma algebra to define measures. Okay, but for outer measure, we use the entire power set. Okay, now in the definition of the power set, we have this. In fact, in general, how many are there? There are three. In fact, there are three. There are these three. I only added this. This is something that I added. But if you look at this, you can see that it takes mu star, which is the outer measure on over X. It takes its value in the interval 0 infinity. But here I'm just stressing that fact. But actually there are three properties, right? It is just to stress the fact that they are positive or they can also be infinity. But these are the actual three. So there are three. If you take this into account, you only need these three properties. Only these three are important. And this one is just to enforce that. So it has to be clear. This property is just to enforce this fact. This. So actually there, 1, 2, 3 properties. That is, mu star of the empty set is 0. If I have 2 elements of the power set, that is 2 subset of X, A being a subset of B, then mu star A is less than or equal to mu star B. And the third property is if you take a sequence of subset of X, we have what we call the sub-additivity or sub-sigma additivity. So mu star of the union of all the AN is less than or equal to the sum of mu star AN. Okay, the remark, what I wrote here, mu star cannot be sigma additive on P X, that is on the entire power set, when X is taken to be R, right? And that result was proved by Vitali in 1905. I hope the date is correct. Okay, so that's what makes the difference between outer measure and a measure because of this property. You don't necessarily have the sigma additivity when you take the entire power set. But with a measure, we have the sigma additivity, right? When you have pairwise disjoint. But here, even if you have pairwise disjoint, you don't necessarily have the equality, right? For arbitrary x. I mean, for any given x. For instance, when x is r, you don't have the additivity, the sigma additivity. You don't have it. But you might have for other sets. It might work for other sets, as you will see in some of the examples that I will give later on. So this is very important. Okay, so so this is an outer measure, which is not necessarily a measure. It's not necessarily a measure. Now we are going to characterize later on measures that we can define from an outer measure. So from this outer measure, how can we make sure that we can construct a measure? Okay, so we will first define what is the Karateridori condition. The Karateridori condition allows us to define what is a measurable set, because remember, here we are using the entire power set. So we need to define what is a measurable set with respect to the outer measure. So an element of the power set that is a subset of X is said to be mu star measurable if it satisfies the Karateridori condition, meaning that this condition is true. That is, for any element of the power set that is for any subset of X, its outer measure is equal to the sum, or is equal to the measure of its intersection with E plus its measure. When I say when I say measure, it is exterior or outer measure is equal to the sum of the outer measure of A intersection E plus outer measure of A intersection E complement. So this should be true for any A subset of X. So if this is true, then we will say that A is measurable. Now, since we have defined what is a measurable mu star measurable set, we can construct the set of all mu star measurable set, and it is denoted by calligraphic M mu star. So a proposition that we will state later on give the result that this is a sigma algebra, right? So M mu star is a sigma algebra. So we are going to see that in the same proposition, that if we take the restriction of mu star, the outer measure, you take the restriction to this M, to this sigma algebra. If it restrict it to the sigma algebra, it will give us a measure. Okay, so some properties of mu star, the outer measure. If two elements A and B are in M of mu star, the union is also there. Right? And you also have the additivity property. That is, if we take two elements in M mu star such that A intersection B is antiset, that is the disjoint. Therefore, mu, the external measure of the union A union B, is equal to the sum of the outer measure of A plus outer measure of B. So you have additivity on M of mu star. Okay, so this Fatou lemma, I can come to this later on. Let me skip and go to the proposition. I will come quickly to this. This Fatou lemma is a property of the measure, right? This is a property of the measure. It is a problem that I gave for you to try to work out, to appreciate your progress in this. But it's not part of outer measure, actually. It's not that much related to outer measure. Okay, so I can skip and come to the result that I just announced, this one. This proposition can also be termed as Karateodori extension theorem. Obviously, it's not exactly that, because in the Karateodori extension theorem, even though we have the same result, but here you are informed that this measure mu, this measure is complete, it's a complete, but I will not go into that. But I'm just mentioning it so that if you watch some video or you read some books, you hear about Karateodori extension theorem, because it's from the Karateodori condition that we define mu star, right? The Karateodori condition is also allow us to define what is a measurable set, right? Comes from Karateodori condition. So what is it? It states that the outer measure, if you have this outer measure on X, M of mu star is a signal algebra, and its restriction to M mu star is a measure. So just to make it simple, that's the result that we have. That's the restriction. The remark is exactly what is already here. I just wrote that to indicate that this definition of mu just indicate that mu is the restriction of the outer measure to M mu star, or M of mu star. Okay, now example, I will quickly give you some example of outer measure. Examples of outer measures. The first example okay, so in the first example, we are going to define so we are taking PR, we take the entire, and we know already that if we take this entire power set, we take X equal to R. So the power set of R, we cannot define a measure on the power set of R. We cannot. So this is a pure outer measure. In some cases, the outer measure will be a measure. Whereas when I say outer measure being a measure, that is on the entire power set, not on the restriction, not on the particular. We are not taking a restriction as indicated by the above proposition. So we consider the entire power set. Okay, so here we are going, okay, it takes its value in this interval, 0, infinity. So this is defined in such a way that at the given point, so here, if I take an element in the power set that is a subset of R, mu star of A mu star of A is defined to be 1, for instance, if X, if A is not empty. Okay, so let's start with 0, where it's empty. So we can say that the measure will be 0. Obviously, it is wise, because we know that one property of outer measure is that if the set is empty, this empty set is 0. So that is if A is the empty set. Now we can take the value 1 if A is not the empty set. So it is it's easy to show that this is an outer measure. So this is an outer measure. So this is an outer measure. It's an outer measure, but not a measure. But not a measure. Okay, to see that, in fact, it's easy to show that you cannot have a sigma additivity. No sigma additivity. It's not possible. Since there are only two values you can see. If you take a sequence that is countable sequence of element, the union will be non-empty, of course. You take a sequence where you have at least one that is non-empty. Because if the rest is empty, it will just be 2. That will be the non-empty and the rest which are empty, which in fact you can say you have 1. Because if you take union with the empty set, it's still that 1. So you take a sequence of non-empty subset of R. So the union will be what? The union will be non-empty. So mu of that union, mu star, of course, mu star of the entire union will be 1 because it's non-empty. So it will be 1. Okay, let me quickly write it here. So, so if I take a sequence like this, so we assume that for any n, an is non-empty. So those that are empty, you just remove them. So we only keep those that are non-empty. Okay, good. So it's obvious that the union that this union is non-empty because it's a union of non-empty sets. So the union is non-empty. So this will imply that mu of the union is 1. It's 1. Now, since also for each one, each one is non-empty, so mu of each will also be 1. So for any n, mu an is 1. So this implies so if you take the infinite sum, of course, when you say countable, you might have finite countable and infinite countable. Okay, if it's finite countable and you take the sum of n, it will give you n, right? So you agree with me that mu, this mu of the union, which is 1, is strictly less, because once you have more than 1 here, it's already 2 and so forth. So it's strictly less than, it cannot even be equal, strictly less than the sum, this sum. So it can be infinity. If you have infinitely many of this, it will be infinity, but still it is less. Okay, so for that it's okay. So it's a measure, but I mean it's an outer measure. It's not a measure, so we don't have this sigma additivity. So that's what I showed here. Okay, so now the second example. We take. Okay, let me quickly. Sorry, I have a class normally with. Okay, very soon I'll be having a class with a part-time numerical student. I will stop very soon, so I need to quickly write this. I didn't know that I will still get at this level. So we are going to define what is the counting measure. Or counting measure. For outer measure. Okay, now this time we take instead of R, we are not taking R, but we take a subset of R, that is Pn. Right? Obviously, we are still using the entire power set. So still from this 0 to infinity, so we have this. And so for a particular set here, we are going to take mu star of A. So we are going to count that we are going to take the cardinality, that's the number of elements, cardinality of A, if it's finite, right? If A finite. And infinity, if A is not finite. So I can say if A infinite, right? Infinite or not finite. Okay, this is counting. We call it counting measure. So it's a measure is an outer measure and is also a measure. So you can prove it. Please try to do that. It's so simple. Try to do the proof. Right. If it's an outer measure, you can also prove that. But particularly the fact that it's a measure, that is this one, show that you have sigma additivity to this. Okay, we'll stop here for today. Thank you so much for your time, your kind attention, your efforts to understand this is really important. But next time, as I said, I will quickly go through what is an integral from this perspective measure theory. And maybe tonight I will continue. I need to complete what I have to say here and wrap up with this and quickly explain. So there's a third example that I will introduce, and from that I will talk about Lebesgue measure, right? Lebesgue output measure, Lebesgue measure, and why we are proceeding this way. Because this idea of output measure came from the way Lebesgue, Henri Lebesgue is the one who formalized all this theory. And in the general theory of measure, they try to mimic, to follow his approach. That's why you have all this. They try to do that. And he's the one who really formalized the LP spaces, all those, Henri Lebesgue is the one who really succeeded to solve the problem that people face with respect to the Riemann integral that was not working for simple cases. Okay, we'll come back to that. Thank you. Bye-bye.